טוב, זה נראה שזה עובד.
לא, להקליט את ההקלטה.
שדרך...
צריך להיות באחרון יש קישור.
כן, אבל נכון. מה הסיסמה?
יוסי ביז 1, 2, 3.
יוסי
ביזי.
לא.
אולי יש עוד גדולה או משהו.
נשים וואי גדולה.
זה יוסי עם שני אס?
רגע, אני מחפשת בדיוק.
לא זוכר.
עשיתי שני אס.
נשים וואי גדולה,
עשיתי וואי גדולה עכשיו?
וואי גדולה, S1, I. כאילו.
וה-BZ גם באותיות גדולות?
לא, קטן, 1, 2, 3.
אינקורקט.
אינקורקט, טוב, אולי זה ל-2, 2, 1.
כן, זה יש לי.
מה הסיסמה? כן. לא, מה הסיסמה של המחשב? לא, יש סיסמה ל-30. כן. אולי זה להשתמש אחר, כאילו לא לעשות 301. לא.
כל כזה כבר ביוטיוב. כן, ביוטיוב.
טוב, אני אלך אליו. אם זה בסוף העולם אז אני לא אלך. כן, פחות.
לא יודע?
כאילו זה אמור להיות הסיסמה. זה אמר לי לא ללכת למזכירות או שלא משנה. מחליט בכל מקרה.
כן, זה ביוטיוב.
שתיים זה יהיה טוב באמצע.
בעיה. זה בעיה.
לא יכול לתת איזה פקטור של 30 נקודות.
30 נקודות לא היה על זה.
25.
לרוב האנשים זה לא היה על זה.
60 נקודות.
תשמעו, אפילו שאלה אחת.
אני עדיין לא מסכים עם התשובות שם. אני לא מסכים עם התשובות שהיא כתבה שם.
איך יש תלות ב-N בכלל?
לא, ברור שיש תלות ב-N, צריכה להיות תלות ב-N.
בניוון? אתה כתבת עם...
לא, בניוון ממש לא, וגם זה הבעיה, שהמצב שהיא התייחסה אליו הוא לא נכון. כי יש תלות בין משולשים.
זה ביוטיוב. הבנתי שביוטיוב זה עובד.
אוקיי. So. Okay, so what we're going to do is to solve the test. Basically, for Moedbet, what I recommend is to make sure you understand this test as good as possible, and to go through those lectures, and you know, like especially stuff that we didn't cover in the tutorial, so you're not sure you know. So just go through it. Make sure that you cover everything. Okay.
Are you saying that with prior information, or are you saying that because just to know?
This is recorded. I cannot say anything. No, just.
Oh, בין חברים, זה בסדר.
No, like I don't know. I think 100% of what you did. Like, I did follow his lectures. But I think there are like few, points that he went through in the lectures, like if he had like some topics or something that we didn't cover in the tutorial. So, just go through it. Like, I'm not saying, start to look for questions or stuff. Just make sure that you covered everything. should be fine. Okay, so question number 1. Okay, so given the following Hamiltonian of antiferromagnet 1 model, so you have this Hamiltonian J Si plus 1, and S2K minus 1. So basically, and so if we only had the first term of the Hamiltonian, then it was just like a regular Ising chain, you know. So we have something like that. 1, 2, 3, 4, etc. And now when we add the second term, so this is basically coupling between all of the odd terms, the odd indices. So between 1 to 3, 1 to 5, etc. So that's how the system looks, but we can draw it in a bit more intuitive way to the rest of the question. You don't have to, like, you know, if you're in a test and you do it like that, you still should be able to like understand the question, but it's just easier to see it that way. So we do like something like that. So this is 1, 2, 3, 4, 5, 6. So this is the first term, and the additional interaction just going to be like that. Okay? So this is just equivalent. So the question is to find the ground state energy and the degeneracy. So if we only had the first term of the Hamiltonian, then because it's an antiferromagnet, then we have, let's say we put the first one to be up, then the second one going to want to go down because it's going to resist the first one, and then up and then down, etc. So this is going to minimize the Hamiltonian. But now we have an additional interaction where all of those couplings are equal, so we're going to have a frustrated system. So it means that if I put the first one to be up, then we have two options. Either this one going to be down and then this one going to be up, or this one going to be up and this one going to be down. And in both options, both options have the same energy, and both options going to be like frustrated system. So in each one of those cases, there's going to be like one interaction term that will be unhappy, because, you know, like if this one up, then this one to be down, but then this one want to be up because of that and down because of that, so it's have to choose which one is going to align with. And then it's going to be the same for each one of the triangles. So it's just going to repeat itself, where each time we fix the first spin. So let's say I fix this one to be up, and then I have two options for each one of those. And then I fix this one to be up or down, and then etc. So for each one of those triangles, we have a contribution of, so we have two couplings going to give me a factor of j. So we have 2j, and one coupling going to give minus j, because it's going to so it's minus, and one going to give me a plus j because they're going to be they're going to be to go to the same direction, right? So if I look at, I don't want to do the purple because I think it's confusing. So this is going to give me minus j, this is going to give me minus j, and this is going to give me j. So overall, just minus j. So this is for any triangle, and then we have overall, the number of triangles is n over 3, right?
But the triangles are connected to each other.
Right, but
It does mean something, because I got lower energy than this in the example.
but still, it doesn't matter because each time you look at one triangle, you look like, okay,
Sure, but you can look at it in another way. You have n minus 1 terms of the first one and n over 2 of the second one. You can just satisfy all the first one and neglect all the second one, and you still get a lower energy.
I'm not sure I understand what you mean. You can like,
Just look at it like an antiferromagnet.
Mhm.
All the first term will give you minus. The
What do you
first
mean
term
the
in the
first?
Hamiltonian.
all of those,
Yes. And all the second one will just not satisfy.
but not necessarily like.
Why not? Just look at it mathematically. Yes, you have two terms. The first term is n minus 1 terms. The second one is n over 2 terms. N is large enough, so n minus 1 is much, much larger than n over 2.
Okay.
So we can just make sure all the first term give you minus sign,
Okay.
and all the second terms you just don't care about it, and you get factor of n over 2.
What do you mean you don't care? Even if all of those give you minus and all of those give you plus,
Yes.
it's
So you
still
have
1 to 2. Like,
you have n over 2, j n over 2, which is lower than n over 3.
okay. Wait. Sorry. You said all of those give you minus, so overall you have an interaction.
n
And
minus
from
1,
here?
not really matter.
N minus 1. Okay. It depends how you look at it, but
Yeah,
I don't
the
think it
same.
should matter.
Yeah, you can just take
And from here you have
n over 2.
n over 2. So okay, we can take a break later and I will look at it, but I think there's a remind me later. Okay. So let's say that's the energy that we got. So overall we have minus Jn over 3. So the second part of the question is about the degeneracy. So as we said, we have for each one of those triangles, if I fix the first spin, so I have two options for the two other spins, either up, down, or down, up. So for each triangle, I'm going to have a contribution of 2, and I have overall n over 3 triangles. So overall, we have approximately 2 to n over 3 states. You can also count the additional factor of 2 for the first spin, but again, it's negligible, so this is approximately going to be the number of states. So this is for the, what is it? A. Okay. So now we're going to use, for B, we're going to have a similar Hamiltonian, but instead of J, we're going to have J over 2. So I'm just going to write it the same. difference is now that because that coupling is weaker compared to the first term of the Hamiltonian, so in the ground state energy, the first term going to dominate. So because this coupling is stronger, then even though the system is technically still frustrated, it's still going to okay, it's not frustrated. It's not frustrated, but like this coupling going to feel frustrated. So the state is still going to be determined only by the first term of the Hamiltonian. So if this is going to be up, then this is always going to be down, and this is always going to be up, etc. So the ground state is going to be just the ground state of a regular antiferromagnet. So we have like up, down, etc. Or down, up, and so on. So the ground state energy so similar to that, we're going to have contribution of minus 2j from the first term of the Hamiltonian plus j over 2 from the frustrated coupling for n over 3 triangles. And the general seed is of course going to be 2 because those are the only options that we have.
Talia,
yeah.
can you explain the generacy point again?
Yeah, so did you understand this one? Okay, so here, because that coupling is weaker compared to the other two, so the ground state only going to be determined by those. So going back to the previous way that we draw it. So all of the spins have coupling J between them, an additional coupling of weaker coupling of J over 2 here. So because this coupling is weaker, we ignore him to determine the ground state. So the ground state is going to be only the ground state of regular antiferromagnet. So if the first one is up, then everyone else is going to be just down, up, etc. And the first one is down, then we're going to have up, down, etc. So those are the only two options that we can have. We don't have, because we don't have the frustrations that give us something more complicated than general C like the first time. So general C just okay. So the last part, yeah.
The frustration happens only in the case then all of interactions are the same, like J, not J and J over some number.
Yeah, basically yes.
Again, I don't agree with the energy. The J over 2 should count n over 2 times, because the number of interactions you have on the second term is n over 2, not n over 3.
In the second term,
K has n over 2 options. It's even given in the question. It's from
Yeah.
1 to n over 2.
so you say if you look from here, or J over 2,
Yes,
there is.
but even if you look at the triangles, you should have n over 2 interactions per second.
See, that comes out negative 3/4 nj. And if in the first case, it also comes out negative n over 2j, which is again still a lower energy for both cases. And with the degeneracy of 2 in both
It's
cases.
even the same antithermal in both cases.
It is regardless.
Okay, I'm missing here something. I need to look at that. Maybe you're right, but I need to look at that.
We can discuss it in the break.
And yeah, okay, I will look at that and I'll tell you. And if that's what you did in the test, I guess you can demand points back.
This is what we did in the test, and we got 0. Oh, the first and part of points in it.
Okay, so back to part C. Okay, so in part C, the question is discuss your finding with respect to the third thermodynamics law. So the whole point here is that so what the third thermodynamics law is say that in zero temperature, which is the case of the ground state energy, the entropy it's either going to be 0 or going to go to a constant that can be taken to 0. So the point here is that in that case, for example, where we have like a normal system, we see that so you remember the entropy is proportional to the log of number of states, so the log of the degeneracy actually. So in that case, we have just some numbers, so the entropy going to go to a constant, which we can take to 0. And in the first case, we have the degeneracy that depends on the size of the system. So that means that we cannot take it to 0 because it's not a number. It's some function of the size of the system. So this is basically an effect of a frustrated system. I don't know if you need to, if that should be part of the explanation, but the whole point is to do this distinction between the entropy of the two states. And that's it.
So
Okay.
the third law of thermodynamics doesn't work to frustrate the systems?
Yeah. So questions besides the energy calculation? The controllers. Okay. Did you try to appeal to Ido about that?
If you can't reach it on
What do you mean?
it on time to email.
But in the in-bar you have something in the in-bar that you can do it through the system, no?
Yes, but it won't help anyone.
Okay. Okay. If that's a thing, like I will talk to him. Like that's.
No, we just want him to be careful when he tries to solve the exam error.
Okay. I'm just happy I'm not part of I'm not checking the test.
בסדר, לא שעה יותר מדי מה לבדוק.
Hmm?
לא היה יותר מדי מה לבדוק.
That's another problem. Okay. So, question 2. So, the Hamiltonian of mean freelizing ferromagnet is given by H is equal to minus J1, sum of I and J. to infinity, and both couplings value taken from some probability distribution. That's just a Gaussian. Okay, so basically what happened here is that we have n spins in the system, and half of them, so for n from 1 to n over 2, let's call this group A, and for I from n over 2 minus 1 until n, we call this group B, just because it's more convenient.
Last one.
Plus 1. So this is A. So for the first term of the Hamiltonian, this is just interaction between all of the spins in group A, and the second term of the Hamiltonian is interaction between all of the spins in group A to all of the spins in group B. So this is just regular mean field, and here we have interaction between A to B, but we don't have interaction within all of the spins in group B. So, and the question is to find the self-consistent equations of the magnetization. Right? So, okay, so basically what we want to do when we have such type of question is to write the Hamiltonian in a form that instead of interaction terms, we're only going to have terms that's equivalent to external field. So it means that I want to write that as something like H effective A S I for I in group A. Minus, and H effective B for I of group B. If we had only the first term, then we only needed like one effective field, but because we have two different types of spin, we need two different expressions. So so I think the confusing point here was with the distribution of J. So actually what happened is that regardless of any of that, when you calculate the partition function and you want to average over J, so unlike the case of like spin class or something where you have J inside of the sum, so J and depends on the index. Here J is just a constant. So when you do this integral, you're just going to get then instead of J1 and J2, you have J10 over n. So when you average over that, you're just going to have J1 average, and then everything else going to be normal. So we just replace J with the average of J.
What do you mean by J10?
This is Ji. So when you average over J1, for example, then you have an integral of J1.
Sure, but you get J0 to when? You don't have a special index inside, or you should.
I think, do you? Yeah, I think you do. Just didn't try it first. This is J I 0. They actually used K, so this is K. This is K. Okay. This is J. Yeah, there was also a mistake that in the test that he had 1 over n, and then it shouldn't have. Okay, so basically what we do is that.
But why can you do it?
Because when you average over anything that includes Hamiltonian, all of that's not going to enter to the
Sure,
not going
but
to enter.
when you are doing the averaging, because it's different where you do the averaging and over what.
The
Because you
partition
don't
function.
necessarily do averaging over h.
You do the partition function. I think like
Yeah,
the,
but the
the
partition
need-
function is e minus. E to
Yeah,
the
so you
minus
have
one
you
factor
have
h.
so you have p of j, and then you have the exponent of beta. Let's take j1 for example. j1 si plus 1. No, it's not. So j. Sorry. It's j. So beside of like something additional, they're just going to give you a constant. Anything that Golti multiplied is, so this is just going to give you e to beta j1 0 over n si sj plus constant. So basically what you say is that this is equivalent to the same Hamiltonian, just replacing.
How can you see this?
Okay. If you have the partition function, si, etc., e beta h, and you want to take the average, p of j, h function is function of j, dj, right? It's like the anneal disorder. So when you
Yeah,
do
but why
this,
can you assume you can use the anneal explanation?
yeah. So because no one asks you for the free energy. Basically, that's like. I would say you should write it more explicitly in such a question, but if you like only had this information, I would say no one asks you for the free energy, so you cannot use quench disorder, because quench disorder is only when someone asks for the free energy. So you compare, like, you know, because the difference between the anneal disorder and the quench disorder is if you average over z.
That over that.
Hmm?
Yes, but it's what the question asked. What was the question?
The question. So the question is like that. Find the equation of states for the magnetization as a function of temperature. And a self-consistent equation for the magnetization of Ising spins. No necessity to calculate the free energy. I'm not saying that it's trivial to understand it from the question. I just explain what was supposed to,
Yeah, but
what
how
we
can
were
you
expected
justify?
to do.
How can you justify it?
Which part? Is this okay? Why can I average over z, or why that's the integral?
No, of course you can average over z, but the average over z is not necessarily z.
Why not? You have this Gaussian. The
Yeah,
Gaussian
but-
take out the average of this, and here you have something that go like Si, Sj.
But the
squared.
weight function in this case is the e to the beta h. It's not just h.
It's that.
It's e to the minus beta. It's not exactly h.
Yeah, it's
So j is not linear. It's exponential.
e to beta. Yeah, everything is inside. You have beta, j, Si, Sj. This is j1 plus beta, j2, Si, Sj. Ignore it like the summation of I and j. So this is the Hamiltonian. It's inside the exponent, but still it's going to extract. This is still going to be the solution. Is this okay?
I'm not sure about that step. I'm not sure.
Start with J1. So technically what you're actually going to have is two integral, one for J1 and one for J2. So let's look at J1. So this is beta h, and this is the Gaussian. So everything is inside the exponent. If you do this integral over J1, you're going to get an exponent. Or
But when you have the exponential, you have Gaussian integral.
right.
But the term which is it's not exponential, it doesn't. It should come actually with quadratic.
Right. That's why I say. Maybe I should do it a bit slower. So you have two terms. One is that, and the other one is something like beta square Si Sj square over something with n. I don't know. But the point is that this one goes as Si S square. So because S is always plus minus 1, this can be ignored. Because this is just a constant.
Sure, but you should only have this term.
No, you also have this one.
If you have the Gaussian integral of e to the minus b x plus
But you also have J1 here.
Sure, but from the integral of j1 you shouldn't have j1 with linear. Only actually j2 with linear term.
Why? If you have
Gaussian integral of
integral of that term, like a x minus x0 square plus bx. So I have linear term here and I have linear term here. So this is going to be up to constant e to b x0 plus b square over 2a, if I'm not mistaken.
oh,
Okay? Okay, so the point is, after averaging, all of the contribution of the distribution of the coupling is that it's going to enter now as we'll replace the coupling with the average of the coupling because of that. We're going to have a similar calculation in the last question, so we can go back to that then. Okay, so the self-consistent part. So we have an Hamiltonian of that form, and we want to write it as an Hamiltonian of that form. So what we want to do is to say we can in general write replace Si with the average of Si, which we call, let's call it Mi, plus some fluctuation. Right? And we define Mi as some, no, we don't define, just the average. Okay, so let's rewrite this Hamiltonian. So in the first term, I and j are basically identical. Like they have identical rule. So we can only we can just expand one of them. We don't need to do it for both. So we do Si. Maybe it's not a good idea to. And then Mj plus delta Sj. Okay? And for the second summation, because I want to get two different expressions eventually for I and j, because I and j, they play different role here. So I'm going to do that for both of them. So I have mi plus delta si multiplied by mj plus delta sj. You can always, of course, do it for si, and then eventually you just take the leading order, but it's just unnecessary. Okay, so that's going to give you minus j10 over n si mj plus si delta si j Okay, so for the first summation, we have two expressions. We can actually only keep the first one, and it should be enough, because we already got something that's linear with si, so we can ignore that.
Why?
Because this is the leading order. Okay, we can keep it for now and then drop it later. For the second summation, the first term is mimj. So this is with the summation. It's still going to give us just a constant. So we can take it out. We can also keep it, and then later in the calculation, when we calculate the average magnetization, this is going to cancel out. So if you're not sure, you can always keep it. So the second and the third are fine, and then the last term is quadratic with the fluctuation. So this is already a higher order, so I'm going to ignore it. So now, what we do is we're going to go back from delta. So delta Si is, we can go back and write it as Si minus Mi. So this is, Si minus Mi. This is Mj minus Sj. So now we're going to do the same as we did here, because everything that is a multiply of Mi and Mj are going to be eventually constant or cancel out of that. So we're going to ignore it, and we're going to just keep everything that's linear with either Si or Sj. So this is going to leave us with J. Okay, let's wait for just a second. Okay, so we have Sj with Mi and Si with Mj, and this is actually what I should have done is either like expand them both or expand none of them. So yeah, so just take the linear order here. Okay. So now the last step before we write a quick effective field is Mi is actually Ma for all of the i's that belong to group A, and it's equal to Si and MB is equal to 1 over n S I for I belong to B. We have n over 2 for each one of the tests. Okay, so now if I want to write it with a stem of the effective field, so we have J10 over n multiplied by, so M, this is going to be MA, n over 2, sum of Si minus so, okay, we have so for this first term, I and J both belong to group A. So I can just change MJ to MA with the factor of from the summation, because this is sum over I and J and this is just the sum of I. And for the second term, we have once MI that belong to group A and one MJ that belong to group B. So I need to split it to two summations, one for A and one for B, with the matching MA and MB. Questions so far?
I have three. First, how is it connected to cavity? Second, where did you see it in the curves? And 3, how you get from this the self-consistency equation.
Slower. The first one, how is it connected to cavity? It's not.
But this is what the question has.
It's a cavity in the question, but it's a cavity here. But I claim it's not cavity. But that's just the title. I don't know what.
So how can you solve this without knowing it's not cavity, but when it's
because you ask for self-consistent equations. So the way that you do it is like a mainstream infield, which is that. Si go to mi plus fluctuation.
Okay, so this leads to the second question. When we saw it in the course,
We did something kind of similar in the last tutorial. Maybe not similar enough, but yeah, I don't know what to tell you. I didn't solve the test. I don't take responsibility.
The last question, how you from this you get to the self-consistent equation?
Yeah, right. I didn't finish the question. It's a bit long, but like so far, we just rewrote the Hamiltonian. This is approximation.
I don't get this is the double summation or the first?
This is a double summation, and this is not. So here, okay, I think it's less confusing if we write it like that.
No. You do want them to be spins. You just summed over the spin.
So what's the?
Can you please write explicitly the first term? Because yes, I mean, how am I supposed to write it as double summation?
Okay, so sum over I for 1, 2, and 2. Then sum over j that is different than I, technically, even that we don't really use it here. Different than I, and go for 1, 2, and over 2, si, mj. And yeah, it's a bit okay. It's a bit. I put myself in a trap here because I defined like mj of the same order of sj. So you can use here like capital M or something, or use here like I don't know average si because like this mj is not the same as ma by like order of magnitude. So yeah, so I do want to stay here with mi, and let's call the new m like maybe capital M. So mi and mj are just the average state of the spin, and those define the summation.
But it should be the same. Since it's the average of the average.
No, but no.
You define mi as the average of si.
Yeah, but mi is like the average state of the spin, of specific spin. So I can have, in this case, we have symmetry, so all of the spins in group A are equivalent and all of the spins in group B are equivalent. So if I write in general mi, it can belong to either one of the groups. So mi is not necessarily equal to ma and mb. If I tell you that I is equal to 1, I know that it belongs to group A. But mi is specific per spin. Okay?
plus or minus 1. So mi it's also plus or minus 1.
Mi is average between
Average of what?
specific. So, okay. It's like, remember that you did like the Monte Carlo simulation or something. So you look at like average magnetization per temperature or something. So if you, what you had here is that basically the equivalent of MA and MB, which is you sum over all of the spins of the system, and then you get something that's may or may not be zero. So another thing that you can do is look at specific spin and its fluctuations in the system and average over that, and that would give you MI. So the reason that we have in the system that we look at like spin S and as like a variable is because we don't know the state of the spin. So what we do is that we say we fix the spin to its average state plus some fluctuation. So this would be easier if we had only one type of spins, and then we don't have to do it that way, and we can just define it with average magnetization that is general. We just call it M. But here, because we have two types of spins, then it has to go like that. So you can think about it in a different way. So like SI is either go to MA plus fluctuation, or MB plus fluctuations, depends if I belong to MB. So you can do like a shorter way. I don't know if that's helped. Okay, so assuming that this is the Hamiltonian that we got, okay, after we finish that, I will go back and I'll show you like maybe a bit faster way to get it. So okay, so assuming this is the Hamiltonian that we got, we can cancel out all of the ends. So this is going to cancel out that. So we get eventually so we only have linear terms of SI. So at that point we can identify the effective fields of each of the spins, and we see that for all of the spins that belong to group B, we can define an effective field, so H effective B, that is equal to J2 over 2 MA. And we can define an effective field for all of the spins that belong to group A, which are those two terms. So this is equal to J1 MA plus J2 over 2 MB. And then the Hamiltonian is minus HA sum of I belong to A minus HB for I belong to B. So everything that we did was just supposed to bring us to that point where we have only Hamiltonian with external field, but not interactions. So how do we calculate the self-consistent equation? So after after we identify an external field, the definition of magnetization, of any magnetization, is a summation over for some spin, let's say Si. So we have Si e to beta h. This is the mechanic. Over some of e beta h. Right, partition function, average. So this is Si e beta h. Okay, so let's separate first for group A. So Si or Si is equal to plus minus 1. So we have beta HA Si, and then we have the second summation, but this summation is on state B, so it's going to cancel out the denominator. So we don't have to count it. So this is over e to beta HA Si, where Si equal plus minus 1. So this is going to give us plus minus, and this is going to give us plus minus. So this is a sine, and this is cosine. So hyperbolic tangents of beta HA. Okay? Positive, negative exponent. So it's easy to see, I think, that for any Hamiltonian that only include the magnetic field, not interaction, this is going to be the result. So we can already do the same for, so this is MA. So we can already do the same.
Capital.
Yeah. We define it like that. So A. And we can do the same for MB. And yeah. So this is hyperbolic tangent of HB beta. And now we can put back HA and HB. So MA is equal to hyperbolic tangents of the affected field of A. So J1 over 2 MA and J2 over 2 MB. And then the same for HB. So we have J2 and A. So we have equation for the magnetization A and the magnetization B as function of the magnetization of A and the magnetization of B. So those are the two self-consistent equations. So questions about the last part. Okay, so before I go to the second part of the question, another, I think, faster way to do that So we got something that's a bit long and annoying in the calculation because of the expansion that we did. So another way is, okay, I look at the Hamiltonian and I see that I need to have like two different self-consistent equations eventually. So instead of do the expansion of m plus delta m, I just divided to effective Hamiltonian for group A and effective Hamiltonian for group B. So what does it mean? So for group A, I want to get something that's linear with the spins of group A. So for the first part, it's relatively easy because they're both, as we say, identical. So I just replace one of them with mi, so mj. And for the second one, so this is basically the same as we did before. So for the second one, instead of expand both of them simultaneously, I say, okay, I want something that's proportional to Si eventually, and I don't care now about Sj from like the Hamiltonian perspective. So I automatically replace Sj with Mj, and I don't care about the fluctuations because this is only the effective Hamiltonian of spin A. So you see that we got something that's linear with Si, and this has already given us the effective field that I erased, but you can see that it's the same. And in the same way for the spins in group B. So here we see that for the first summation, they're not going to contribute anything because they only relate to the spins in group A. So we only look at the first summation, and again, Si belongs to group A, so we don't care about the fluctuations of it. So we look at Mi and then Sj, where J belongs to group B. So this is just, it's not that much shorter, but maybe it's a bit less confusing than go through the expansion, the fluctuations of Si. So, and then you get the effective field of A from that, and the effective field of B from that. So they're just done a little bit shorter. So for part B of the question, after we got the self-consistent equation for M A and B, so it's in case of the system undergoes a finite temperature phase transition, find the transition temperature and critical exponent beta. So this is kind of similar to, a bit more similar to what we did with like I think saddle point and unknown theory and all of that. So that's not specific to Okay, so first we're going to find the critical temperature, and then we're going to expand around the critical temperature to find the critical exponent of the magnetization. So around the phase transition point, we know that the magnetization is going to be approximately 0. That.
Can you repeat?
So around the temperature, the critical temperature, the magnetization is going to go to 0. So we want the first order of magnetization around 0. So for each of those equations, we're going to expand them around small values of MA and MB. So for the first order, MA is approximately beta J1 over 2, MA plus beta J2 over 2 MB. And MB approximately beta J2 over 2 MA. Okay, so we have.
Can you repeat the question? What?
Okay, we want to find the critical temperature.
The,
So we want to around the critical temperature, the magnetization is going to be very, very small. So we expand the two self-consistent equations that we found around 0. And basically what we want to do is we want to find a solution that is not m equal to 0.
not what?
That is not m equal to 0. Right? Around the phase transition, we have that we go from that to that.
So in this case, you just want to solve the two equations.
Hmm?
So here you just want to solve the two equations.
I want to find the critical temperature, which means the value of beta that solve this equation around 0.
So you just want to solve those two linear equations.
Yeah, I just want to solve those two. So for we just plug MB into MA, so this is going to give us beta J1 over 2 MA plus beta square J2 square over 4 MA, and all of that equal to MA. So we say that we want the non-zero solution, so we can divide everything by MA. So, and then we get 1 equal beta J1 beta square J2 square over 4. And then we get that the critical value of beta is minus
J1. Which is the plus.
Hmm?
Plus, because you have minus 1. And you need a factor of this.
J1 squared over 4.
You can multiply your okay.
Make assumptions.
Hello.
Yeah, and of course, this is equal to 1 over. Okay, so this is the critical temperature.
And you should take the plus.
Yeah, and you should take the plus to get something positive. Okay, so now to the critical exponent. So we want, we know that around the phase transition, the magnetization go as the T minus the critical temperature to beta, and we want to find beta. So again, what we do is we expand around the critical temperature the magnetization, so MA, but now we're going to have to expand to additional order, because you remember that we did with Landau theory, so we have like the expansion of like the free energy, and we always had to take 2 orders. So we're going to keep something that depends on M. So we're going to go back to the hyperbolic tangents and expand it to additional order. So M will not cancel out. So we have tangents hyperbolic of beta J1 over 2 MA and I'm going to already put.
I think you should switch to different constants since you have beta in both cases. You
Yeah,
you
we have
search for
we
the
have
beta in
beta.
exponent and you have beta from the critical.
Yeah.
It's not the same beta. Just call it K1.
So let's define beta ji equal ki. Okay. So we have ki over 2 ma plus, we're going to use again that for, because the first order we can just expand the tangent to the back. So we're going to have k2 square over 4 ma. It's the same thing as I did here. So just for simplicity, to not lose factors on the way, which I'm definitely going to do, let's define all of that as some function c. So c is a function of temperature multiplied by ma. So if we expand it around small value of m, so we get c ma minus c cube ma cube over 3, and etc. etc.
Why minus?
Hyperbolic tangents with minus in the extension, no? Yes. How do I have?
It's exponent of plus not minus.
It's x minus q.
No, it's just exponent plus minus exponent minus. So all the even terms just cancel out. All the terms thing should be plus.
I think it should be fine.
Anyway,
Okay.
how do you know that you can just plug MB and it won't affect more than the terms that comes from the multiplication of MA and MB?
You can expand that to higher orders and then put the higher orders here and see that eventually they're going to give you even higher orders. And I just assume that it's what that you can do like the extra step. You can put the tangents here and then expand the tangents. And then you have expansion of expansion. Okay, so we cancel again MA, and we're going to stay with 1 C minus C square C cube MA square, and instead of putting back the all of the constant in C, because we saw that the critical temperature is kind of ugly and we don't want to expand around it. So C is actually the thing that's solved. So C for T equal the critical temperature is equal to 1, because that is the thing that we expanded before. This is CMA. So when T equal to the critical temperature, this was equal to MA. So this is just, you can just use that expansion. So when you rewrite that, you have, so this is equal.
You need some temperature dependence.
C depends on the temperature.
Yeah, but you just want to take it to be 1.
No, I'm not going to plug that in. I'm just going to, I'll show in a second. Ignore that for a second. What did I want you to do? So that's eventually we get that MA is equal to square root of 3C minus 1 C cubed. I didn't do a mistake. So this is just the solution of that. And now, because we said that around the critical temperature C is going to be equal to 1, so we see that this expansion is actually proportional to square root of T minus Tc.
Why?
After constant, because this is what we got here.
No. You don't have T minus T.
This is the, so
You
okay.
just says it sees 1 at the critical temperature, so C minus 1 should be of order T minus T6.
yes, C
It's a bit
is
fishy
that,
because you
all
don't
of
know.
that, right? So it's proportional to the critical value of B. So if you have, yeah, I'm sorry for the mess. So C is equal to B critical multiplied by something plus other something equal to 1.
But the other something is the beta critical square.
Right. But the first order. So if you look here, so you have, let's see, so you have one something that go as 1 over critical beta minus 1. Sorry, 1 over the critical beta minus 1. So this is 1 over Tc minus 1. So you multiply everything by Tc, so 1 minus Tc over stuff because everything entered to C. This is doesn't have minus anything. So in the first order, it's have to stay that. So you're still going to get something that's sorry, I forgot units.
What about the C cubed? You just assume it's small.
Hmm?
And what about the C cubed? You just assume it's small.
What?
C cubed.
Cube? What is cube?
C to the
Oh, cube.
cube, yes.
No,
That'll be
C
close
to
to
the
1.
cube. It's like if you have something that's go like T cube or Tc cube. If you don't have something minus something, then this is always going to be the first order. You need to have something that's proportional to the difference between T to the critical T. So you know you have a function of the temperature, and you want to expand it. So if you take that to the first order, then just give you 0.
Okay, so again to the denominator, from where you got the T, because you have the
Yeah.
critical minus 1.
So see. Okay. Equal 1. Maybe it's actually easier to just put everything explicitly. So just put it explicit, it will be easier. I don't know. Okay, so one option is to put all of the constant back and expand around that. Another option, but maybe I need to check with you though if that's a legit answer to. Because, okay, what you get here is you get that beta is equal half, which is what you will get from a normal ferromagnet. So basically you can claim that because the first order of the interaction is just the regular main field that we usually have, and then you have additional interaction with the second group. But you also have the regular ferromagnet, so you should have for the first order something that behaves like regular ferromagnet. So this is like the regular critical exponent.
But you don't know that the interaction with the other group are small. Maybe
no, I'm not. I don't
the
mean first order like small. I mean that like first order in like distance. So, but I'm not sure. I need to ask you about that.
And when you find beta, shouldn't you divide and find beta for the other group as well?
Yeah, so the assumption is that they're both in the same order of magnitude, because by the first order, and if you don't want to do this assumption, you can put this back in MB and go through the same thing, but you can basically claim that it's the same order of magnitude, which you get if you expand it to first order. So, because this is something of order 1, and
you expand the first one for a linear term and a cubic term,
yeah,
and then you plug back to the second term. Then you just take the linear term. It should be of the same order.
yeah, and yeah. So when you so we just except of the contribution of the critical temperature, the couplings are all of order 1. I think it's also given in the equation somewhere. So both magnetization should be the same order, which is I think another justification to why that should be the same as ferromagnet. Yeah. Okay. So. Do you want to break before the last question? Yes? Okay, so let's take 10, 15? 10 minutes.
Can we talk right now about the first question? מה שאני אומר זה דבר כזה. נניח יש לנו פה אין פחות אחד או אין פעמים אינטראקציות,
לא, אני חושבת שהבנתי את הנקודה שלך וזה נשמע לי הגיוני.
וזה גם יוצא פחות.
כן, כן. ואני מנסה להבין אז למה זה...
כי יש אינטראקציות זה לזה, ואז פה יש לנו פחות דרגות חופש, כי זה קיבלנו את זה. מהמשולש הקודם קיבלנו את זה. אז אנחנו לא באמת יכולים לבחור את זה שוב.
לא, אבל אתה מדבר על האנרגיה, לא על האנרגיה.
אבל זה לא זה ביחד. שבגלל שאנחנו זה, אז אנחנו לא צריכים לספור את זה, אנחנו סופרים את זה בצורה אחרת. אנחנו אמורים גם בצורת משולש להצליח להגיע לאותה אנרגיה, אבל אנחנו צריכים לצפור את זה מה שאנחנו עושים. Do you want to switch to English so you will be able to understand
something, yeah.
Yeah, that will be easy. Do you understand what they do?
Yeah, that's it's much less energy contribution from the second one than the first one. So
Because you have
So-
much less terms, at least less than other.
Okay, so let's look at this configuration.
That's the yes, that's the anti-ferromagnet configuration, and then what you got.
כן,
So
זה
it's
קצת
first,
יחסית שנה.
or will it just be
Mine.
mine? And then
Here
addition,
you get n over 2 times plus,
מכוון לאזור
because only plus.
yeah. So
כן, זה בעיה.
times
יוני כזה, סוף יוני, תחילת יוני.
you have n over 2 numbers.
וגם תוכלו להכניס את זה. לא לימודים, שכן.
For each triangle we have minus 2j on this.
שלישי ליולי. בקורס הבחינה.
I understand why it's not sufficient. You don't have another 3 triangles. Because this triangle doesn't start from 7 or 6, it starts from 5. You actually have n over 2. Because each triangle has one point from the previous triangle.
Yeah.
So for large enough n, you have n over 2
No,
triangles.
you're absolutely
And then you get exactly the same answer.
absolutely right.
And then you get what should be anti-ferromagnet.
אני בפרידת לכם עודד.
בשניהם?
כאילו לא בזמן. בזה ובשיטות.
But it doesn't affect on illustrations.
I'm not sure.
לא אומר את זה.
Maybe, yeah, maybe
שלמה כזה שכולם כולם מסתכלו על איש.
no, it should affect the general feedback. I'm not sure how exactly. I need to think about it.
Yeah, I think you're right. When I initially sent the solution to Ido, I sent that.
שאלה קשה.
That's for the second part. And then,
אני רואה את
yeah,
זה
that's what you said, right? For the,
Yeah, that's what
yeah. Yeah, you're right.
About the degeneracy, maybe I'm not sure about the degeneracy because
So the degeneracy, okay, so basically now the difference that what I thought is that it will be like that, with n over 2 instead of n over 3 for each triangle. But you use it for something else?
yeah, but I'm not sure if I need some steps because I just said it's anti-ferromagnet, so you have the degeneracy is 2, but maybe I thought of other cases like what we used it.
Yeah, but
As we see here, should result in the same energy. Yeah, yes, maybe the states used here result in the same energy, so the degeneracy should be. Right? No, I'm not sure. Something like that.
that's because you have the first one.
Yeah, that's it. So, I know that.
Why it's not true?
Because the state she showed us when you can just switch the terms, switch the spins and get the same energy for this triangle, and then you can just extend it to all the triangles. they result in the same energy. So all of the states have the same ground energy, just like antiferromagnetic, which is actually one solution of the form she gave.
I believe the mistake is that we don't know how to count triangles. So
No, you can just
if that was a main
can be
problem in the
confusing.
test, you should definitely get to the point. I don't know if that's I understood that the average was like
I think the second and the third question was were the main problems, not the first one. I mean, even if you get all points from the first question, so
You can still fail due to the other question. Still, you want to be accurate.
yeah, for mode bit I talked to the dog about the test, and for mode bit he did show the test, so we should be fine.
Hopefully.
because it was very
And if there is something like that and you don't get answer from the door, so like I don't know, talk to me, talk to you, talk to anyone, I don't know, but
because it was fine that in order to prepare the test we solved some problems, but then I opened my test, I didn't see any of those,
yeah.
so it was nice to prepare. Yeah.
I usually do the preparation tutorial after I see the test, and then I can do something that's like somehow relevant. Yeah, I'll do this now.
So the first test is relevant to the second.
To the second test. Yeah, but I do recommend to go through with the test.
You mean for all of it, or only the last part about cavity and yield?
I think that there was some topics. I don't know which point of the course it was, but there were like some topics that, like you don't need to go through like transfer metrics or you know, stuff like that. I think maybe in the last lecture, I think there was something that he did that was not related to the tutorial. There was also something that he did with like solving the Eisenhower with like recursive solution. Now that you have like the partition function for like n+1 particles, and then you
Yes.
The replica.
No.
The replica.
no, I don't. It's not replica. It's a thing that you
Yeah.
come before.
Yes.
So there's also that.
In the middle.
No, I think it's solved this due for solving the replica method.
No, it's not.
We just split it to all the systems.
No, you have something that looks similar to replica, but you also have something like that for
Yes.
like just regular 1D icing.
Oh, it is
So it
really
should come early.
Yeah,
in
yeah,
the
yeah.
middle of the course, yeah.
So yeah, I know
Before
that.
we show the transfer matrix, and so if we don't want to do this, we want to do transfer matrix instead.
Yeah, but you know, so that stuff like that, just take a look so that you know, like.
So I think he should just, he is going to give us to develop things from the lecture.
Oh, that-
And like yeah, we do the test.
And about the battery, are we going about this? Because we still haven't written this formally and rigorously, mathematically.
Yeah, I still think you can just explain it from physical perspective, but I would ask you about that if you want to tell you something that's, you know, I think you can still do that. I just maybe I will like write it more organized and I will ask you
I think we would be glad for that because we don't know, we missed here, we don't know what, how to find this explicitly.
אז זה מעבר פאזה. המבחן שלנו לעומתה. המבחני הבא.
אז איפה טמפרטורה קריטית יש שונה קריטית.
שנראה לי בית אמור להיות חיים. כן, בית זה מלא נקודות. רק על המשפט הזה. רק על המשפט הזה. או שכן צריך. שאמרתי שנראה לי שבית צריך לתת חצי. ככה.
כמה נקודות הוא נתן לך על זה?
מה?
כמה נקודות הוא נתן לך?
נותן לי 10. רק על זה.
אז בגלל שעשיתי 3 מהשאלה עשיתי נכון קיבלתי.
מה? באמת?
עשיתי את כל הדברים האלה, כולל לכתוב את ה-H אפקטיב, כל הדברים האלה.
אני כתבתי לו,
כי זה מה שזכרתי שהוא עשה
חלוקה
בקלאפטר.
לחלוקה ואתה נכנס לקודות.
אצלי אין וקיבלתי 15. הגעתי לבית השווה ל-0 וכתבתי לו שלדעתי יש טעות בכל הפיתוח.
אני אפרם לו גם לפני זה, זה לא קשור.
כן, אין פתר.
יהיה עוד פעם, בכל בית. יש לי הרגשה.
יכול להיות שהכתב שלך לא היה כל כך ברור?
אפשר
לא,
לבקש ממנו אולי שנעשה
איך אתה יכול להיות? אם כתבת כאילו
מה נעשה?
משהו דומה לזה.
אני מיציתי עבודות.
הוא היה
לא אכפת.
כאילו, כל בכלל לא למדתי, צריך לעשות מבחן.
אני גם, אני חרבשתי את זה. עשיתי בכלל פיתוח סאדל פוינט, כאילו, לא...
אני גם עשיתי סאדל פוינט והתערבתי מהג'יי, אמרתי אני לא יודעת מה לעשות, אני אעשה מה שאני יודעת, אני אתעלם מכל הנתונים של השאלה.
אני אעשה את כל החלק הזה של הממוצע וכל הדברים האלה.
כאילו, יש שם X על השאלה, לא יודע, הכל X, אבל 15 נקודות.
שיהיה בריא.
נדע.
וואלה, אפילו שאלה ראשונה. מה זה רחוק היה מהתשובות? למה?
כן, היה שם טעות גם.
היה שם טוב.
בעיה.
זה מה שהוא אמר, מה שהוא אמר.
האנרגיה שאמרתי לך.
שזה 0.2?
כן, כן, עכשיו הסברתי לך
זהו,
למה. וגם למה במשולשים מגיעים לכל
כמה יוצא? מעניין, אולי צדקתי שם.
כי מה אין חלקי 2?
זה אנרגיה יותר נמוכה, כאילו.
נכון. היא פשוט פספסה במשולשים. כי היא ספרה כאילו יש חלקי 3 משולשים, אבל זה לא כמות משולשים שיש.
מה התשובה?
מה, מינוס J?
נכון, גם לי יצא שם.
זה
אני
מה שאמרו
חושבת
לי.
שגם אני כתבתי.
זה התשובה
כן.
הנכונה.
טוב, בסדר, זה לא יעזור לי.
כן, זה מה שכתבתי. ומה יוצא בסעיף ב'?
בסעיף ב' 3
גם לי.
כן, זה מה שאני...
אז אני צדקתי.
גם, אבל עדיין, אני לא
גם
מגיעה
אני.
ל-60.
אני צריכה עוד 25 נקודות.
זה לא מה שיעשה את ההבדל.
אני מגיעה ל-65.
למה? קיבלתי רק 10 נקודות על השאלה, מגיע לי עוד 10.
לא, פחות מ-60.
ועוד פקטור 15 נקודות. אפילו בקוונטים היה 2 נקודות פקטור, אני לא יודעת. 2 נקודות?
כאילו, פשוט
הוא
פשוט...
רצה שכולם יעשו מועד ב'. הוא
הוא
אמר את זה.
עצמו טען. כאילו,
כן,
אם הרי
טען.
צדקתם על...
תודה.
מי?
טליה ואישרה את זה מולו, ולהפך טליה אמרה לי שזה מה שהיא שלחה לו בהתחלה, והוא אמר לה לא.
כן?
יואו.
נשאל לשאול אותו.
אני רוצה.
זה היא ענתה לי, היא ענתה לי.
כן,
לא
ממש.
אני חושבת שיש פה מחדל רציני.
זה אחד מבין רבים במבחן הזה.
אבל אם לא הקימו ועדת חקירה ממלכתית
ראית עכשיו איך היא פתרה את השאלה השנייה וגם לא סיימה לפתור אותה? משהו מזה למדנו?
אני לא אומרת...
משהו מתוך... לא, משהו
היא
מתוך
לימדה
זה
אותי,
למדנו
נראה לי
בקורס.
בשורה השלישית.
לא, לא,
גם
לא.
באמת
זה
כולנו
אנחנו.
היינו בהרצאות.
היינו בכל ההרצאות.
היינו בהרצאות, אני מרגישה שאני בכל ההרצאות.
אני לא מבינה מאיפה הוא הביא את ה-H אפקטיב הזה.
כן,
עשינו משהו דומה פעם?
לא, יופי, תודה, אני שמחה לשמוע את כל הרגשתי שזה רק אני.
זה פשוט לא
אני
נורא.
חושב שהציונים מדברים בעד עצמם בשביל זה.
לא,
שלא צריך להעביר זה לא
מי מתאר את המצגת?
לא, זה כמה שבעיה. לא מבין קורס מתמטי עם מצגת.
שאלה פה אחת.
אין מקום לשאול.
תאמיני לי, אני כותב הרבה יותר שעות ממנו על לוח בשבוע ומסתדרים.
הוא פי 3 ממך בגיל.
לא, אני חושבת שהבעיה היא
לא דרשתי ממנו לעמוד וללכת. יכול לכתוב על טאבלט.
עדיין,
זה לא כזה הרבה.
אין לו גיר לגרוע.
אין לי בעיה.
ואנחנו אומרים פעם מה היינו? זה הפתיחה שלו.
מה?
יש לו שם את ה... קורא לי... נתקדם על הבדיחה הזאת שלו. אצלנו זה היה איך אומרים 3 פעמים. זה היה הרבה.
Okay, so For the last question, we have a correction to make. So about the energy in the first question. So we had the Hamiltonian, right, SI, SI plus 1. So I was wrong, and the energy, if you look at the triangles, okay, so one way to do that, as I said, is to look at the Hamiltonian, and if we assume some state of the system, so we have up, down, etc. So we can look at the Hamiltonian and say that we have n interactions from here. So we have factor of nj, and we have n over 2 interactions from here. So we have minus, sorry, this is minus and this is plus, n over 2j from here. So the overall energy is minus n over 2j, which is different than what I got. And the reason they did match with the calculation from the triangles is because there are no n over 3 triangles, but n over 2. Because apparently we don't know how to count, neither do we do. So yeah, so you see it because of the way the indices are arranged. So the number of triangles is going to be actually lower, and then it's going to align with this calculation. So that was a mistake, and I will update the solution in the model and talk to Ido. So okay, so that was for question 1. So now for the last question. So the Hamiltonian of 1D random field Ising model. So we have, in that case, both random interaction and random field. So we have J, I, S, I plus 1 minus H, I, S, I. And both Ji and Hy and Hi are taken from Gaussian distribution, but Hi taken from distribution with average of 0. So we have E minus Hi squared over 2 and Ji. Okay, so first part of the question, find an explicit expression for the free energy under the annealed approximation. Find also the ground state under this assumption. So we need to find the free energy and the ground state. So as a reminder, the free energy is proportional to the logarithm of the partition function. So if we use annealed disorder or annealed approximation, so f is equal to minus log average of z, And for the quench disorder, which is the second part of the question, f is average of the log of z. So he wants the first option, so we want to calculate the average of the partition function. Okay, so in general, we remember the partition function is defined with the exponent of beta h and sum over all of the spin states. Yes. So this average is average over the random variables that are h and j. So the average of z is an integral over dj and an integral over h e beta ji si plus 1 plus beta hi si. So this is just for the partition function.
Should be some.
And p of h and p
No.
of j.
Why some? It should be odd if you put just
Yeah, but we have some of the states and products over time. So this is from the partition function, and we have from h and j plus, so minus hi square over 2 minus j0 square over 2 and 1 over 2 pi. Okay, so we have two integrals that are that we can separate because the field only appear here and here, and j only appear here and here. So the two integrals that we need to solve are integral. dh e beta h si minus hi square over 2 and an integral dj e beta j si plus 1 minus j0 square over 2. So the integral that we're going to use is actually the integral that I wrote earlier on the board. So for ax minus x0 plus 2x
squared.
square. So the solution will give us some factor that we don't care for now, and we see in a second why. E beta bx0 minus b square over 2a. So let's start with the integral over h. So because the average of this Gaussian is 0, we see that we're only going to get the second term. So we have something that's proportional to E beta square si square over 2. I think it should be 4.
Yes, should be 4.
So, okay, so I'll go back to in a minute to what that is. And the second integral going to give us e to beta j0 si plus 1 plus beta square si plus 1 square over 2. So now we remember that the spin si is equal to plus minus 1 because it's a Cannon model. So both si square and si plus 1 square is going to be equal to 1. So this is actually equal to e beta square over 2, and this is e beta square over 2 as well. So now we're going to put everything back. So we have everything that relates to the summation of the partition function. And we're going to all of the intervals done. So we stay with e beta j0 si plus 1, and also e beta square.
But we have also constants from the integral.
Yeah, and we also have some factors here outside. So,
But the factors can have significance because, for example, in the Gaussian integral, you have factor of 1 over the square root of a, which in this case